Plane gradient descent has a problem. In a long, narrow valley, it zigzags across the steep walls while barely creeping along the flat floor. And near a saddle point, it can slow almost to a standstill. Momentum and atom are the two optimizers that fix this. By the end of this video, you'll see, in 3 dimensions, exactly why they're faster and more reliable, and what's actually happening under the hood. Here's the trouble. This lost surface is a ravine. Steep in one direction, nearly flat in the other. Standard gradient descent takes a step proportional to the slope, so it overreacts to the steep walls. The result is this wasteful zigzag. Most of the motion is sideways, bouncing between the walls, while the direction we actually care about, down the valley, barely advances at all. Momentum borrows an idea from physics. Instead of stepping in the raw gradient direction, picture a heavy ball rolling downhill. It builds up velocity, and that velocity carries it forward, smoothing out the bouncing. The update keeps a running velocity. New velocity equals beta times the old velocity, minus the learning rate times the gradient. Then we move the weights by that velocity. Beta, usually about 0.9, sets how much past motion we keep. Watch the difference. The oscillations across the walls cancel out, because they keep flipping direction. But the steady push down the valley adds up step after step, building real speed. So the ball accelerates along the useful direction and damps the useless one. It reaches the minimum far faster, and glides straight through small bumps and saddle points that would trap plane gradient descent. Atom adds a second idea. Adapt the step size for every parameter separately. Directions with consistently large gradients get smaller steps, and flat directions with tiny gradients get larger steps. It does this by tracking the average squared gradient in each direction, then dividing the step by its square root. Steep directions are damped automatically, flat ones are amplified, with no hand tuning required. Atom combines both tricks. Keeps a momentum term, m, the running average of the gradient, and a variance term, v, the running average of the squared gradient. A small bias correction fixes their startup values. The final step divides the momentum by the square root of the variance. That single update gives smooth, self-scaling steps, which is why Atom is the default optimizer for most deep learning today. Now the moment of truth. 3 balls, the same starting point, the same surface. In blue, plane gradient descent. In gold, momentum. In green, atom. Watch them go. Gradient descent zigzags and lags behind. Momentum surges down the valley. And atom carves the cleanest, most direct line to the minimum. Same problem, 3 very different journeys. So the sense behind it is simple. Momentum remembers where you were going and builds speed. Atom adds per direction step sizes, so no single dimension dominates. Together they make training faster and far more stable. Plane gradient descent is the foundation, but momentum and atom are what make modern deep learning practical. Subscribe, and next we'll visualize how a neural network bends a decision boundary to separate data.